Good evening, everybody. So let us start our lecture tonight, and today is October 19th, and according to our syllabus, and this week we will discuss. We will start graph. Okay, and then basis of today we will discuss basis of BFS and DFS, breadth first search and depth first search. Okay. So, let me open the slide. So in my previous section I recorded, but I forgot to save the file, so it was not saved. So this lecture will work for both sections, I believe. Okay, I found this slide online. So it says elementary graph algorithms. It's really elementary graph algorithms. So because if you take advanced algorithm course, same book, in future, then you will see that there are more algorithms and then more different kind of graphs and the difficult. And this in this course we will discuss the foundation only. And also I believe if you took data structure course, it should be covered in data structure course, basic graphs algorithm should be covered in data structure course. Okay, so like a tree, okay, a graph is also a non-linear data structure. Linear data structure means starting from array, linked list, stack, and QE. So elements are somehow linked, linearly linked one after another. So here in tree and graphs, these are non-linear data structures. So elements are connected, but not that like in a linked list are connected. Okay, we will see the basis. So this is mathematical definition of a graph. Is a G is a function, is a G, okay, is a set of V is a set of vector is vertices, and E is a set of edges. Okay, and edge means the connection between one node to another node. Here a vertice means a node. Okay, and when you discuss a tree, that we saw that a tree has a root. Tree has a root, then parent, children, parent, children, parent, children, this way, right? So here, so in a graph there is no root, but we call them, the node is called vertex, and if there are usually more than one vertices, and actually there is no like root. So it has source and destination, starting point and ending point, and any node can be source, any node can be destination. Okay, and the connection between two nodes, the link between two nodes is called edge, and edge. So there are multiple edges. Okay, and as we are familiar with like some apps like GPS apps. So GPS apps use graphs in the behind. So it's starting from a source or one point, it shows direction to another point. Okay. Sometime, so graphs, let me show you the picture. This is a graph. These are nodes A, B, C, and D. There is no parent-children relationship. Okay, but each node is called vertex, and these are edges. This is an edge, this is an edge, this is an edge. Okay, and Edge means connection. If the connection can be directional, one unidirectional or bidirectional. So this is there is, if there is the connection is unidirectional, then there will be an arrow. But there is no arrow, that means bidirectional. So there is path between A to B and also B to A. So in mathematical definition we say unidirectional if undirected graph, if the edge, if there is an edge between A, U, V, that means the connection between node U and V, if it exists, and if it is equal to V to U, connection from V to U, for all V, okay, there such that V comma V, that means there is, this is the pair, okay. So this is V comma V, this is a pair, this is called self loops. We will see the self loops soon, okay. And directed if there exists a direction from U to V, but its inverse does not exist, but that is called directed graph, okay. So we will see some, okay. And then weighted graph for each is if there are some weight or cost or profit or loss or distance, okay, then this graph, that graph is called weighted graph. For instance, the in a search tree, BST or trees, we saw that there is a connection between parent and children, right? Those are connection are just link. It does not say how much a parent loves his or her child or children, right? There is no such barometer, okay. That's this connection, okay. But it will show in a graph, it will show how much it costs or how much it loves, or how strongly or loosely or how it is they are connected. This is the weight. For instance, in a GPS system, we see the direction. When we see direction, it also shows us the distance from one place to another place, okay. So in a graph from one node to another one node, that means one vertex to another vertex, it shows the distance from one node to another node. These are actually weight, or sometimes it may be weight, it may be actual weight of some items, or it can be distance, or it can be profit or loss or gain, whatever cost, okay. So a graph is said to be a dense graph. That means it means if it is all nodes are connected with all other nodes. So in a dense graph, the number of edges, that means the length of the set of E is pretty equal to V squared. How many V is the vertices, how many is this connection. For instance, if I have so if there is a graph like this, if there is a graph like this, these are connected, these are connected, these are connected, these are connected to each other. So here there is 1, 2, 3, 4, 5, 6 connections, right? Here 1, 2, 3, 4, 5 and 6 connections. So number of edges over here, so you say E here equal to 6, okay. And here is V squared, how many vertices, 1, 2, 3 and 4, okay. And then 4 squared, so 6. So we know that 6 less than 4 squared, that means 16, okay. But in a sparse graph, that means not all nodes are connected to each other, there are some non-connection, non-direction, Okay, that this means. Okay, and the efficiency in terms of, for instance, this is for complexity, time complexity. So in case we will see that some algorithm, some applications using graph algorithm, that in this case the worst case complexity will be big O of v squared. This here you see that uppercase and lowercase v's. Uppercase means the set and lowercase means is individual edge or vertex. So two vertices are said to be adjacent if there is a connection between them. Okay, if there is no connection, they are not said to be adjacent, no matter how far or close they exist. For instance, if we have one node, two nodes, another node over here, okay, another node over here, so they are connection over here. Okay, I'm sorry. Okay. So if they are connected over here, they are connected. So they are connected here. They seems to be close, but they are not connected. So these are not, A and B are not adjacent, but A and C are adjacent. I'm sorry, B and C are adjacent. Here I so B and C are adjacent, and so A and D are adjacent. They are connected. Okay, but B and D are not, and C and D are not. Okay, graph is said to be a connected graph if there exists a path between all pairs of vertices. For instance, this is not a connected graph because there is no path between B and D. So if we add a path between here, and if we add path from A and B, and also A and C, and also D and C, then it will be a connected graph. Is fully connected. Okay. Okay. So now how a graph is represented in programming perspective or in computer memory. So a graph can be represented in two ways. One is using an adjacency list, another is adjacency matrix. So adjacency list is like a linked list. Okay, for instance, here you see that A, B, and C and D. These are the nodes A, B, C, and D. These are the vertices. Okay, and here there will be small linked list over here. This A list will be connected. For instance, it will say what are the other vertices that this A vertex is connected to. So A has connection with B, right? Okay, and then like this is the A has connection with D, and A has connection with C. Okay, the figure it shows the linked list. It seems to be A is connected to B and B is connected to D, and D is connected to C. It's not like this, like this. Think about like this way. Here A is connected to B and A is connected to D, okay, and A is connected to C, and similarly B is connected to A, B is connected to A, and B is connected to C. B is connected to A and B is connected to C. And similarly, D is connected to A and D is connected to C. D is connected to A and D is connected to C. Order is not a factor, so you can write D, B, C. What is order? That is not a factor. Okay. And there is another way to represent graphs. It is in adjacency, like adjacency matrix. So a matrix is a two-dimensional array. So for instance, you can say A, B, C, D, or they give also additional number 1, 2, 3, 4. So with this word you can give like text. Okay. This is for A, this is for B, this is for C, and this is for D, and this is for A, B, C, and D. So if there is a path or connection between A to B, then we will put 1. 1 means there is a path, and 0 means there is no path. If there is no path between A to B, then we put there 0. For instance, there is no path between B to D, so there is no path between B to D. So here from B to D or D to B, whatever you say, this is 0, that means there is no path. Okay, and here for diagonal, this is diagonal 0, 0, 0, this is a diagonal path. So if sometime you will see that there is a loop, this is a loop. If there is something like this loop, so then from A to A there is a path. That means we will say that 1 over here. There's A to A. A has a loop, self-connected. But here it is not self-connected, right? It is not self-connected. So there is no path from A to A. Okay. Oh, sorry, I forgot. There are few announcements. Okay, I published grade for other section in assignment 2. Maybe tonight or tomorrow I will publish your section's assignment grades. Okay, so your test, according to our schedule, your test will be next lecture, right? Next lecture there will be test. We will take it during your class time. So there is no class. You can come here or you can take test from anywhere place or anywhere, but it is okay. Your you need to be self-responsible. It is your responsibility to have good computer internet connection. If you lose internet connection, I have nothing to do. Okay, so hope you'll be fine. So make sure that you have enough charge. Okay, and take it during your lecture time. So I will open. It will be open 15 minutes before test time, but you have to start before our class time ends. You have to, if you start at even 7:40, that should be fine, but please do not wait for the last minute. Okay, and the test will be open book, open note, but without any device. So do not try to open other device from other side. Okay, so it catch video, so it will take, so the webcam will capture your video every moment. Okay, what else? I forgot. Okay, let us go. Okay, that's it. Adjacency graph and adjacency matrix. Okay. Storage requirements, then how much memory it takes. Okay. So for a graph, it takes theta means plus minus, what pretty same thing, pretty or what in usual case, average case. Okay, number of V plus E. V is the set of vertices and E is the set of edges. Okay, and now let us. So this is pros and cons of graphs. I do not see any cons, but this is really useful. You will see that there are some applications. You will maybe not next lecture. Next lecture we have a test, but after the test we will see that some useful algorithm of use of graph. So I don't see any cons from my side. Okay, I covered this one. Adjacency list, adjacency matrix, and space is V squared. Okay, one thing is that. Okay, the two things we need to understand. First of graph searching algorithm. There are two kinds of searching algorithm. One is called breadth first search, another called is depth first search. Okay, so you have to understand this and give attention, please. I think it will not be more difficult, that much difficult. So first of all is breadth first search. So let us see the definition. Okay, so let us think that we have a graph G of V and E, either directed or non-directed, it's not a matter, and we have a source vertex. As I said that in a graph there is no parent or there is no root. In a graph usually you will have a source and you may have a destination. You may not have a destination, but you must have a source. Source is the starting point. Okay, but unlike a tree, in a graph any vertex can be source. Okay, that is the difference. Okay, and here the output will be say d of V is equal to distance. Okay, that is the smallest number of edges or shortest path, okay, from source to a vertex V for all V belongs to V, and if there is no path from one, okay, that means yes, that is from one vertex to itself. For instance, d of if there is no path from one vertex to another vertex, so that we put that infinite in symbol, infinite symbol, or in programming either a very large number or a negative numbers, for instance outlier. We denote that if there is no path. Okay, and let us see an example. For instance, so this is breadth first search, it is shown over here. Let me show you this one. So in order to understand graphs searching, so what is the purpose of searching? To search for a specific element, right? Okay, so we know that in a binary search tree or a linked list or a tree, or we saw that if our search element does not exist, or if it is the last element, then how do we search it? We say big O of n, right? And here it will be big O of number of V. So we need to search all vertices. Okay, and one thing is that, so we do this searching becomes two ways. One is called breadth first search, another called is depth first search. Breadth first search is easy to remember. Okay, depth first search is a little bit complicated. So let us understand easiest one, the breadth first search algorithm. And before we understand these in terms of graph, let us understand this in terms of a tree, mainly a BST. For instance, let us think that we have a BST, like we have BST like 7, and then 5, 6, and then 4, and then right side 8, maybe 9, this 9, and then this side 10, and this side 8. It's a simple BST, right? It's a simple BST, and we know that a tree has a root, so this is the root, right? So how do we do BST with B breadth first search? Okay, this is actually, you know, in traversing, remember the traverse, the 3 kind of traversal, right, for a tree. One is called in order, another is called pre-order, another is called post-order. So here BSF is pre-order, pre-order traversal, like a pre-order traversal. So how do we do pre-order traversal? So if you do pre-order traversal, right, so that means we know we need I'm sorry, no, I cannot say pre-order. Let me see. I will see if it is applicable. The OA of breadth first search is that you start one level, you complete that level. So this 7. So it will come 7 first, and then you start second level and you complete this 5, 9, 7, 5, and then 9, and then you come this level and complete this. So 9, like 4, 6, 8, 10. Okay, and also that this you can go also 7, or you can go 7, and then instead of 5, 9, you can say 9, 5. Okay, and then so here there is two variations, right? Then 4, 6, 8, and 10, and also you can have other variation for this part, right? So other order, so you can say 6, you can start 6, 6, 4, 8, 10, you can say 8, 8, 6, 4, 10, or you can say 10, 8, 6, 4, 10, 4. There are various order over here, right? So if you consider order, if order is a factor, then you can this case. Okay, so that then does it mean pre-order or post-order? In like prefix or infix or postfix traversal? No, right? Okay, then I should not write it. Okay. So start a node, start a level, and complete it. Okay. So the breadth first search is easy. Okay. So compared to depth first search, it is more difficult. There are depth first search. There are 3 kinds of depth first search. One is the in order, pre-order, and post-order. So depth first search, I can say D depth first search in order, and depth first search pre-order, and depth first search post-order. Okay. So now tell me, please. You know that how to traverse a list, right? This is also tree, BST. Okay, so in order, that means how do we start that? So the root will be inside, in between two left and right children, right? Okay, so A is 7, we'll skip 7, then we'll go 4, 5, we'll skip 5, then we'll say 4, right? 4, 5, 6, right? This is an easy one. 4, 5, then 6, 1, and then 7, right? Then 7, and then here tell me please which order will come from the right subtree. We are searching from in order. That means every parent will be inside or between left and right children, right? So 7 will be between 8 and 9, right? So 9 will be between 8 and 10, right? That means 8, 9 and 10. And then 8, 9 and 10. Okay, so we can get this by 3. You have a question?
Yeah, so what if the right subtree had something that was deeper than the left subtree? Because in order is only checking the left subtree first, so that technically wouldn't be depth first if the right side was deeper.
That's not a problem. So right side go more all the way in. So if it has more, right? You are taking that. This one is so let us see the 16. 16 will work over here. 16, and then let me say 14, and then let's say 20. This will not be a complete, although it is not a full, or this is not be a complete subtree, right? Actually, it comes like this way. If you want to add, okay, it's okay. Let us see, and then 15 is this way, and maybe 13 here, right? So what is your question? What is your problem? If I have this, so here then I will go here also. Then I will say 13, 14, 15, then 16, 20.
Right, but because it's in order, so it would still start by going to the left subtree and getting 4 first. And so even though like 13 and 15 are on a deeper level than 4 and 6 on the left side.
Yeah, we have to start. This is the branch, left branch, and this is right tree, the entire. So we have to, this is the left branch, and this entire is right branch. This entire is right branch. So we have to complete this left branch first.
Yeah, but the right side is deeper.
No, that's not our issue. It's not a problem.
Doesn't matter.
No.
Okay.
That doesn't matter. We have to follow those. That's true. Just follow the rules. So what do you like me to go with this one or the previous one? So you got your answer, right? Do you understand what is his question? So he said, yeah, he said even if this is unbalanced tree, right? In case of unbalanced tree, what will happen? Still, do we need to say left side? We have to give priority first, left side. Yes.
Oh, I just wanted to say to him, I think it's more, it's the direction of breadth or the direction of depth rather than go to the deepest node first.
Okay. I got it.
So let me go back to okay. Now you know the pre-order. Tell me the pre-order one, please. Which one will come first? Yes, 7, right? 7, then 5, then 4, 6. So you have to complete this branch first. Okay, then yeah, 9, 8, 10. Is everybody okay? Madam, are you okay? Okay. Then the first order. Hmm? Yes. Post order, that means your root will be later, right? All the way in. Okay? Children will be first. So what are left children is first. So then it will come over here, skip it, then go over here, skip it, and then 4, 6, 5. Okay, 4, 6, 5. Okay, then 8, 10, 9. 8, 10, 9. Then 7. So now is clear, everybody? So one thing is that for any searching algorithm, any searching process, there is no way that it will go the right child first. It never starts with 10 first. This is in terms of, we are talking about tree. This is a tree, this is not a graph. Please don't mislead it. Okay? But I brought it here so that we easily understand the depth first and depth first search processes. Okay? So here how is the breadth first search algorithm process? Breadth first is start one level and complete that level. This is one level, right? Root level, then first level, second level, or whatever level you say. Start one level, complete this. Start one level, complete this. Okay. So if we understand this, like searching, okay, at the end of this searching, what is our purpose? What we will gain? What we will find? A single node, right? Okay, so then complexity will be big O n over here, right? In terms of n is the number of nodes, right? Or in terms of graph, if we say is the number of vertices, so the big V, uppercase V, right? Not n over here. So V denotes the number of all sets. Okay. So that means in the worst case, we have to check for all vertices, all nodes, right? Either maybe we'll be looking for 10, so 10 will go all the way end, right? Or you are looking for 12 or 11 that does not exist. Still, we have to search for all existing elements. So in the worst case, we need to go all the way in. So now, has anyone question about depth first search? If it is okay. So if you understand this, then it will be easy to understand depth first search in terms of graphs. But that is a little bit complicated, more complicated, a little bit complicated. But let us think that we understand the foundation or basis of depth first search. Does anyone has any question? Okay, now let us recall the difference between a tree and a graph. This could be a graph, right? This also could be a graph. So, but whenever this is a tree, we say that this has a root. Okay, but if it is not a tree, then we say that it has no root, but it has a source. Source can be 7, source can be 5, source can be 9. Okay, any node can be source. So in that case, the difficulty is a little bit difficult, but this is the foundation. If you understand this, hopefully the next slides will be easy. Okay. Now let us understand the easy one. Breadth first search for a, this is a graph, right? We are no longer discussing tree, but let us convert this in a tree. So this is a graph, right? Okay. So let us convert this. So this side is a graph. This side a graph. So let us convert it to a tree. How can I convert a tree? If we rotate 90 degree, so then we can say this x is over here. Okay, and then it has two children, right? M and P. So one side is M, another side is P, and it has another child, that is Y. Okay, and Y has 3, right? This side 1, 2, and 3. And one side N, another side G, and another is Q. Now it is a tree, right? We can draw this way like a tree, right? We can say this is a tree, right? We can think about this is also, we are considering this is a tree-like graph. Do you have same connections? Yes, right? We do have same connections and we do have same ages, same number of ages. Now let us try to understand how do we do breadth first search traversal. Okay, and then as we said that there is no root, but we have a starting point, right? Starting point can be anything. It can start from Y. Okay, it can start from X. So if we start from X, then how do we do the breadth first search algorithm? Starting from X, like consider that this is the base level. This is the root level. Okay, so then take X first, then take X first, and then the second level. Go to the second level, right? What the second level? P, Y, and M, right? And then take P, Y, M. Okay, but if it is order, then you can say P, Y, M is one order, and or M, Y, P is another order, and then Y, P, M another order, Y, M, P another order. So recall that a minute ago, whenever we discuss depth first search for a tree, we did not go from right to left, right? The largest one, but we went for sometimes in order and pre-order, post-order, right? So consider that way. So for instance, starting from X, then we need to go P, this second level, this level, and it can have multiple orders. So it can have P, Y, M, or it can have P, M, Y, multiple direction. You can, if you start from P, then come this way, or if you start from M, Y, come this way or this way. So this is why there are variation, but starting point is X. Okay, so then we are covering P, M, and then whenever you come at Y. So then when we come at Y, right, then Y has tails, right? Another level. So in this level, then how many variations are there? N, G, Q, right? Or it can be G, N, Q, and then this will precede. This time will precede, and the last few will be, you can say N, G, Q, or you can say G, N, Q, or you can say Q, G, N. If the order is a factor, if there is no factor, then it's easy. You can say, well, it's one thing, N, G, Q is fine. But what is spatial? Spatial over here, start one level and complete that level. Okay, so now let us see that what is the incorrect BSF breadth first search traversal. If you understand some incorrect traversal, then we will understand, right? If you understand why it is incorrect, then we should understand what is correct. So for this one, what is incorrect over here? For the first one, why it is incorrect? Adam.
Up and down the levels and missing, not hitting the children.
So which one is missing over here? Which one is disorder?
Second one or first one?
First one. First one. Which one? We are starting from X.
You need a P in that first one.
Sorry?
P would need in that first X, P, Y, or.
So X is fine, right?
Right.
Then coming Y is fine, right?
You need
And
to
then-
P or M, not Z.
And the problem is over here, right?
Yeah.
G. It should not come G first, right?
Yeah.
G is the third level, right? Do you understand? Problem is here G. This is the problematic. First problem is, right? It may have multiple other problems. We are, for instance, okay. So then, how about this one? Oh, there is multiple PP over here. There is a. What is the problem over here? For instance, this is only one P. Okay. What is the problem here?
Q is before M.
X and Y is fine, right? And Q is coming before M, right? That is a problem. Q is this is making problem. Is everybody okay? Let me fix it. Okay, so now we consider starting point X. We may consider starting point Y also, right? In that case, the sequence will be different. Okay, if you start from Y, then tell me someone. It's easy though. If we start from Y. Who can help me? You want to start from Y? Yes.
It would go Y, X with two children, MP, and then.
Y? Y?
Oh, you just want the order?
Yes.
We could do like something like Y, Z, N, Q, X, MP.
Yes, then Y, the first level, right?
Yeah.
It has second level. N, G, Q, this is second level, right?
Yeah.
And these are the P and M are third level.
Yes.
See that? So if you hang on this, then this will go either here, right? P will go here and then M will go over here. Okay? So if you start from Y, right? This is the first level, this is the first level, and this is second level, and this will be this second level, also this one, right? And this is another level. So maybe if you draw a circular, maybe that may work. Circular path. So it can start anyway. For instance, from in your GPS system, your GPS app, when you use it, right? We can start from any location. We can have a starting point, right? And we can expect any location. This is our destination. Here we are considering starting. Is okay, everybody? Okay, now let us take a break for the depth first search is a little bit complicated. Why the depth first search is a little bit complicated? As I said, okay, the following few slides, it shows the colorful some images. So the directions. So for instance, if you start from S, starting point or source, then you see that these are black. That means you need to cover first this adjacency edges you need to cover. Then you need to go any edge, then you need to cover that adjacency edges. So then you need to cover that adjacency edges. This is the way. So please go through this slides, okay? And then here we have the algorithm. The book has also algorithm. So if we analyze this algorithm, for instance, the algorithm, we mainly our main target will be finding the complexity of the algorithm. Okay. So in the complexity of the algorithm, for instance, as we saw that, what will be in the worst case complexity? Big O n. Big O not n is v. Uppercase v, okay. Lowercase v it means over here a single element, single node, okay. And uppercase v is the set of all vertices, okay. And infinity means the path does not exist. And while you do program, then we cannot write infinite, so that you will put a very large number, okay. Now, so this is the illustration from according to the algorithm. According to the algorithm, if there is no path, then we say put infinite in the value. Yes, it's the illustration according to the algorithm. You can go through these slides, please. Okay, go through these slides. How to find this? This is the good slides, colorful. Then you will see how this. So we have a few more minutes. Let me do the complicated one. Then you will cover this the depth first search algorithm. Okay. So as we saw a few minutes ago, the depth first is a little bit complicated even for a tree, right? So for a graph, it will be a little bit more complicated, since in a tree we have a root and it does not have root, but it has source, and any point can be source, right? We are considering source here as x, right? And then the source can be y. Okay, so for instance, this is the point. Now I am waiting and I need a direction. I start my GPS from this point, or I can go this point and then I can start my GPS, right? At any point I can start. I may have my starting point. So for instance, for this graph, so since there is no fixed start point, it can be any start point. So based on the starting point, we will have our source point. We will have different order. Okay. Now similar thing. If you draw this, if you flip this, rotate this 90 degree, and then you will get a tree, right? Corresponding tree, and you can draw. So for instance, now starting from x, and here the depth first search algorithm, it follows actually pre-order traversal, like pre-order traversal. Let us see whether it does exactly or not. So how do pre-order traversal does? If it is our AC starting point, this is a, we are considering that this is a parent, but this is not a parent. There is no parent. It's source. Okay. Then we will start from S, right? And then how does a pre-order goes? It goes from the level, right? Down, 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 right? So then X, then Y, right? And then at this point, Y has 1, 2, and 3, right? 3 vertices, and it can go any order. So first it start from X, then it will go Y, and then it will complete N, G, and Q in any order. So N, G, Q, N, Q, G, or Q, N, G. So there can be 3 variations over here. You understand? Is okay, everybody? So the goal will be starting from here. Oh, if we rotate it, then we can draw maybe something. If we rotate and if we draw the corresponding tree, then we will have X, and then M, and then P, and then Y, and then N, and then G, and then say P, let me say Q, G, and N. Okay, now starting from X. Okay, depth, go the depth. Okay, in the breadth first search algorithm, what did we do? We started from on point and we went to this, we completed that level. Okay, wall nearby adjacent vertices, and then we went to the second one, right? But here is not that. Go on the depth from starting from X, then Y, right? So this is this X, Y, and then you can say there are three variations will be over here. Q, you can say Q G N, or you can say G Q N, or you can say G N Q, right? So this is why there are three G N Q, or G Q N, or Q N G. There are three. Then as many depth as we have, if you have another one, for instance, like W over here, then after G you need to go W, right? If do you have this, right? And after G you need to go W before you come to P and M. So when you finish these ones, but I'm not getting this. So when you finish this level, okay, then come back to P and M, right? And if it is order is factored, then there are two orders over here, right? You can say P1 or you can say M1. Okay, so you can say P, M, or P. So there may have multiple directions, more sequence over here, right? So for these three, there will be 3 times 2, right? One for P, another for M, another for M, another for P. There will be more variations over here. But let us understand some wrong or incorrect depth first search traversal. We hope that if we understand incorrect, then if we can correct it, then we'll be able to know, right? What is the process? What is the mistake over here? You know, say, what is the mistake? What is the fast travel over here? I'm asking him. Yes.
The L is in the wrong place because it's not a child.
M1, right? It is making issue, right? Okay, M should not come first, right?
Yes.
Okay, then thank you. Someone else from this side. Elmish, that's your name, right? Okay, tell me what is the mistake here? There may be multiple mistakes. I'm looking for the first occurrence of incorrect. So X is fine, right? Then Y is fine, right? Then G is fine, right? Then what is wrong over here? Yes, again this M is making, right? So then if we get rid of this M, then let us see. Then P is in right position? Let us write this x, y, g. Then what should be next?
Anybody?
Yeah,
Q or N?
yeah, can try. Yeah.
Q or N, right?
Yes, either q or n. Okay, then what is next?
P or M.
Yeah, and then p and m, right? Because we have left p and m. Then in one error, you can say p or m. We may say this error, right? This symbol maybe say these or this or this or this. Okay, one thing is that, for instance, if you are asked to write this, first count how many vertices are here. 3, 3, 6 plus 7, right? And make sure that in the answer it has 7. Okay, the first you need to check that on. You have 7 message. That, for instance, you should not have more or less, exactly 7. In the test or in the assignment, if you are asked to write the depth first and breadth first, like searching error, you don't need to write hundreds. Okay, you need to write a few. Okay, or I will specify that at least this many. Okay, has anyone any question? You have a question?
Are we gonna do the traversals with our adjacency matrices as well? Or are we just gonna do the graphical portion?
Okay, one thing is that we did not go through that. Maybe next time we'll go. So in a graph, it can contain multiple adjacency matrices.
Yes.
So for instance, whenever we use our GPS, right? Sometimes you see that it shows that some route is the shortest distance. And some route it shows in gray color, it shows that the shortest time, maybe, right? For instance, maybe short is from here to downtown. Okay, maybe distance, maybe in the through a highway, maybe distance is large, not shortest, right? Shortest may be directed, but it will take more time. Okay, but sometimes shortest distance takes more time. We know that, right? And sometimes like longest distance, longest time takes less distance. Okay, that's it. So for instance, a graph can contain multiple adjacency matrices.
Yeah, my question was just if we're given, like, will we be given the adjacency matrix and then have to perform a search on it?
Yeah, so then there are some algorithms, but there are some applications actually. Salesman's application. For instance, how does a salesman do work? Or a distributor, Amazon distributor, or post office, postman, carrier distribution, how they do? So they need to distribute all materials, right? And sometimes they need to save time, or sometimes they need to save their mileage, gas. So what order they should go? We will have some problems, salesman. So there are two process, greedy algorithm, and we will see that there are some application. Good question. We will discuss this. Those are the applications, the real applications of graph. But one obvious application that we are familiar with, the GPS system, is the graph. And in that case, you will be given the OA. At the beginning you saw that weighted graph. Weight will be given. The weight maybe it can be distance, okay, or it can be, for instance, profit or loss or cost, right? Or sometimes, for instance, let us think that if there is a path, also there is a path over here. There is an edge over here. Think about maybe this is a breeze, okay? It's a high breeze quality new breeze, and it has $100 tax or toll. Or rather, it has $10 tax and a $20 tax toll, right? We may consider that, oh, I don't have, time is not a factor for me, but I can save some money if I go this direction, toll fee, right? Instead of going this direct direction. So all these are considered. There are some good applications. We will see that at the end of this. Maybe next week we'll see. from graph algorithm. This is why I said that if you take advanced algorithm course, most of the advanced algorithm, and there are a lot of new research are going on graphs. So another application, for instance, in data processing, if you want to count all household items in the USA, okay, and then from where should you start with? From New York, or DC, or California, or Atlanta? Where should I, right? You can start from any position, right? So that would be different variation. Okay, so that's all for tonight, and please be ready for the upcoming test. Give me 2 more minutes, please. Let me check my attendance. Does anyone has any question though?
Yes, sir.
Okay.